Well, let me start by thanking the organizers for putting together a wonderful conference. I think it's about time that we have conferences involving all signs of lambda. So I wish it was in person, but okay, we'll get there. Now, the purpose of this talk is to just make some very brief remarks about the topic of Disidio space-time from my own perspective. I will try to include various ideas. I will be brief in the detail. I will try to build a bit of panoramic view of explorations. And if I've omitted any particular topic, it's not necessarily because I don't find it interesting, but rather it's because of my own lack of expertise on that topic. It's very difficult to do a review on these subjects, and we can reserve topics that I don't discuss for the discussion session or the gather world. Okay, so now right. So let me just start by discussing the outline and motivation of the talk. I mean, there's a lot of people in this in the audience that have worked on positive cosmological constant or find it interesting, but I'd like to just go over an outline of the kind of topics that I'm going to discuss. And but let me start with a very brief motivation. So the motivation, as far as I'm concerned, if we're studying positive cosmological constant, is that to reasonable approximation, or very good approximation even, it seems to be relevant to questions regarding the early phase of the universe and the late time structure of the universe. And this is recent observations that we've come to know and trust more and more in the last 20-25 years. And based on that, I think we have now clear guidance from the experimental world as to what flavor of space-time might be worth focusing on and understanding in detail. And remarkably, both the early phase of the universe as well as the late time structure of the universe having to do with Disidio, a proper understanding seems to not just require classical features of this space-time, but rather quantum features as well. And the reason I mention quantum features is because this is the kind of problem we care about from the theoretical physics perspective rather than purely the phenomenological perspective. But the reason we require quantum features in the early universe is that it may involve physics at very high energies, or even the nature of quantum fluctuations in expanding space-time. And the reason that we care about quantum properties of expanding spacetimes in the late time structure of the universe is that it seems to be intricately connected to the question of horizons. And as we've learned in the last 25 or 30 years and even more, understanding the nature of horizons, certainly in the black hole context, requires us to properly incorporate quantum effects into the discussion. And those two issues, sort of high energies or quantum fluctuations and horizons, are inextricably linked to the question of a proper description, to the necessity, to the proper description of these kind of positive lambda or approximately positive lambda spacetimes. And so that summarizes, at least from my perspective, the necessity to study such spacetimes and the urgency to study such spacetimes, I would say. It's no longer an open question what the shape of the universe looks like, at least to first approximation for the foreseeable future and in its earliest phase. Okay. Good. So having said that, the three topics I'd like to review in this talk fall roughly under the following categories. I'd like to discuss first some basic features of the geometry and group theory associated to these spacetimes. And from a theoretical perspective, I'm going to take the idealized version of these quasi-de Sitter universes. I'm going to consider them to be in their purest form, exact exponentially expanding spacetimes, and those go under the name de Sitter space. So that is the spacetime driven by a positive constant vacuum energy that is eternal. So we will take this as our approximation of what we mean by an expanding spacetime. And the second type of physics I will review is physics related to the Sitter horizons. And in particular, I will focus on properties of the Sitter spacetimes, the Euclidean signature. Now, there have been several talks already in this workshop where Euclidean methods have played a prominent role, such things as the Euclidean path integral, particularly in theories of gravity. And it seems that they will play no lesser of a role in the context of the Sitter type spacetimes. And so I think it's an important part of the discussion. And so I'd like to emphasize that. And it's often a discussion that isn't emphasized heavily in traditional cosmological treatment, but from a theoretical perspective, the Euclidean signature question may be of particular importance. And the third part of the talk is related to a quest, an ongoing quest to try and identify controllable at the mathematical level models of such spacetimes in contexts where we forego any phenomenological relevance. And so in this context, we will allow ourselves to veer off into other dimensionalities. And perhaps to some degree, again, touching on questions related to previous talks, we will afford ourselves the freedom to work in 3 and even 2-dimensional spacetimes. And you see, recently, there has been a lot of exciting work based on 2-dimensional models for black holes. And I see no reason why similar excitement and insight may not be gained in the context of cosmology. But of course, this is from a very theoretical perspective rather than a phenomenological perspective. My attitude is that as we collect more data, we will be able to make more precise phenomenological statements. But in the meantime, there are essential theoretical questions that we need to address. And for those, we can give ourselves the liberty of being more creative about the spectrum of particles or the space-time dimensionality. So that concludes my apology for the topics chosen here. And having said that, I guess, unless there are any questions regarding the motivation or structure of the talk, let me proceed into the details of the various subsections. So I'll pause for a few seconds to see if there are any questions. And please, oh yeah, in the spirit of all the talks so far, since I cannot interrupt myself, please interrupt me. Yeah. Okay. So, good. So let's proceed first by reminding you or showing you the nature of the geometry and some aspects, some group theoretical aspects. Okay. Now, let's start with the basics. So in its most complete form, the geometry that we will be discussing is a geometry that happens to admit a coordinate chart covering the full manifold. These are the coordinates over here where t ranges across the full real line. And this is just a round metric on the D sphere. So this is the D+1 dimensional universe. And you note that in the far past and in the far future, you have an exponentially growing spatial sphere, okay, that shrinks to some finite size in the middle of the space and then grows again. And already the nature of the geometry teaches us that there are some crucial differences between the types of geometries that we may be accustomed to thinking about. For instance, there is no natural notion of a spatial infinity. In fact, the constant time slice is compact, and so there's no spatial boundary. There's no natural notion of null infinity. All null and time-like geodesics end in the future boundary or the past boundary of the space. And so it's difficult to cook up or think about traditional notions of the Nernst matrix in this type of space-time. On the other hand, the space-time is maximally symmetric. And so it's endowed with a very large symmetry group. And it would seem wise to try and organize physics in terms of an organizing principle that crucially rests on this type of maximal symmetry group. And in the case of the Disidio universe, this symmetry group is SOD plus 1, 1, which you may be familiar with from the perspective of Euclidean conformal field theory in d-1 dimensions, little d-1 dimensions. So it's the same, for example, that, to put it prosaically, and since Parisi won the Nobel Prize today, the symmetry group of four-dimensional Disidio universe is the same as the symmetry group of the critical point of the three-dimensional Ising model. This is a large symmetry group. It's as large as it can be at the level of isometries. And so it would be good to organize physics with regards to this symmetry group. And one more statement that is good to make is that if we project or push this symmetry group all the way to the future boundary, it subsumes into the conformal group acting on the sphere itself, perhaps somewhat reminiscent of the discussion of Andrea on the celestial sphere and the role of SL2C in her discussion. So this is the basic setup. This is the world that one would like to explore. And in order to do so, I think it's important and traditionally not heavily emphasized to understand in a clear way the role of these symmetries, okay? As they are our one whole, they're one sort of organizing principle on how to think about the problem. So what does it mean? So let me proceed that. What does it mean to think about these symmetries? Well, we have to ask ourselves the kind of question we ask ourselves in quantum field theory. And a very natural question, as we're dealing with the Lorentzian spacetime, is what kind of unitary reducible representations do we have associated with this group? And these, fortunately, have been classified by the mathematics community some time ago, particularly due to seminal work of Harish Chandra, amongst others. And just to give you a flavor for the type of representations present for this non-compact Lie algebra, we can take the physical case of d equal 3, so four-dimensional Disidio, in which case they come in three flavors. They come in the form of what's known as principal series, where the parameter labeling the scaling dimension, or the SO1, 1 subgroup, is given by a complex number with a very specific form, which is known as the principal series representation. Again, yeah.
Hi. So these are the unitary representations of the group. That's true. The only one that is lacking is the trivial one, the identity. Would you relate this to the vacuum of the theory somehow or not?
Yes, yes. If you want, yes. The identity is the trivial representation. It's the only representation that's allowed to be finite dimensional. And you would say that the vacuum state, provided that a quantum field theory in a fixed de Sitter background preserves a de Sitter invariant state, or contains in its Hilbert space a de Sitter invariant state, this state would be indeed in the identity.
So then suppose you are considering the three-dimensional de Sitter case, and you are hoping to have some kind of duality, like holography. Would you say that the dual CFT in that case, whether it is or not unitary, we have the vacuum as a normalizable state?
So you got cut. I'm sorry. I don't.
Sorry. Suppose
could you repeat the question?
Once again, about the vacuum. Suppose now you are in three-dimensional de Sitter space, and you are hoping to have some kind of holography.
Pure gravity in 3 dimensions.
Sorry?
Are you thinking about pure gravity in 3 dimensions, or a more elaborate setup?
No, let's say pure. Let's put some matter to have local degrees of freedom if you want, but it doesn't matter.
Okay. Yeah, yeah.
The question is, would you expect the dual CFT, which is 2-dimensional in that case, whether or not it's unitary, to have a normalizable vacuum or not? Related to this question about the unitary representation as a vacuum of the theory.
The problem, I would start at an even more basic question, because I'm not sure that the structure we should be after is a CFT at all. You see, my problem is the following, and we'll get to this, but let me already anticipate the answer. what I think is related to the answer, which is that in a theory of gravity, in fact, since the isometries of Disidio are part of the diffeomorphism group, it seems that we need to gauge them as well. And so ultimately, in a theory of gravity, it seems that no state should transform under anything but the trivial representation. And so whatever the description is, it has to be built out of Disidio invariant states, because if they were covariant under the Disidio group, they would break the diffeomorphism invariance. And so the traditional picture of DSCFT seems to avoid this question, but it doesn't answer this question in a clear way. You see, we're not allowed to put boundary conditions, at least in traditional physics, in the far future. And so we are not allowed to freeze the metric in the far future, and we're not allowed to freeze the gauge transformations in the far future. And so we have to gauge all symmetry, all diffeomorphisms, including the isometry. And so I would say everything, all states in a theory of gravity and Disidio, if there is such a thing at the quantum level, have to be Disidio invariant. And so it's just part of the description. So I hope that since all states are Disidio invariant, have to be Disidio invariant, that some of them will be normalizable or have a good, well-defined inner product. Yeah, I think it's a very good question. Now, the discussion here, just to be clear, is at the level of quantum fields in a fixed Disidio background, in which case we're not gauging the diffeomorphism group and we're allowed to carry non-trivial representations. And at that level, it is indeed the case, at least for heavy fields in a clear way, but seemingly also for light fields, that they admit a Disidio invariant state in their Hilbert space. And that would transform under the trivial representation, and it is normalized. Is that okay? Can I keep that as the answer for now?
Yeah.
Thank you. All right.
Thank you.
Yeah. Now, to add some more technical detail to the discussion, I should say, and we're going to hear more about this, I assume, in future talks and discussions. It's not just the representations that have been classified for the Disidio group, but rather one can compute in detailed form various group theoretic quantities, and one of these quantities in particular is the reduced group character of the Disidio group. And I just mentioned these kind of things to show you that there's quantitative data about the organization of these infinite continuous representations, which are unbounded. So they're nasty creatures from the perspective of traditional representations we study in quantum field theory, but nonetheless, they really do have concrete and meaningful expressions. For instance, the group character, which we'll use a little later in our discussion of the principal series representation, though continuous and unbounded, which is here represented by the fact that we have an integral over a continuous parameter across the full real line, can be computed in a meaningful way, and one obtains a very simple looking expression for the character as a function of this Gothic T over here. So these are expressions that are known. These are expressions that mathematicians have understood. They've understood how to resolve the continuous nature and unbounded nature of these representations. And as we'll see a little later, these are expressions that contain a remarkable amount of physical content in regards to quantum fields in Disidio spacetimes. So I just wanted to make that technical point here before proceeding. Now let me pause again to see if there are any questions. And if not, let me note that the characters of the Disidio group are not merely analytic continuations of the characters in ADS. They are of a different nature. For instance, they involve things like shadow operators, among other things. And so one should be very careful when pondering about the relationship of Disidio space and anti-Disidio space at the level of analytic continuation. That's just a side remark. Okay. Okay, so now, with a sort of discussion of the symmetries at a slightly more sophisticated level than what is often the case in the literature, but not always, we can ponder precisely this question of Gaston about what is the relation between conformal field theory and eternal inflation. And in fact, this was pondered early on in various papers. And at the level of quantum fields, in a fixed de Sitter background, or perhaps even linearized fluctuations of gravitational fields, but effectively treating them as fields in a background de Sitter, there are some implications at the level of certain expectation values, namely at late times, the profiles of field operators transform nicely under conformal transformations. They look like conformal primaries under the Sitter group. At the free level, we can in fact associate to these late time profiles unitary reducible representations of the de Sitter group, and fields, different types of fields, such as heavy fields or light fields with respect to the de Sitter scale, which is set to 1 in this talk, or gauge fields, naturally fall under different categories of these representations. And correlations or expectation values of insertions of local operators at the late time boundary naturally obey the ward identities and constraints ensuing from conformal field theory considerations. This is all at the level of symmetry. And rather remarkably, although, just a brief historical remark here, although from the perspective of conformal field theory, a very basic and essential correlation function is the 4-point function, because it's the starting point of, say, the crossing equation and the bootstrap picture. The first computations, as far as I can tell, and I would love to be corrected, of 4-point functions with 4 operators inserted at the late time boundary don't go back much earlier than 2006, even though the notion of quantum field theory in de Sitter spacetimes or inflationary spacetimes was appreciated since the 80s at least. The first, or the 70s even, the first computations of 4-point functions of the late time boundary with a true exchange in the interior of space come much later. And that shows perhaps a little bit the difference between the mindset of conformal field theory and focusing on conformal symmetries versus the traditional type of calculations we do in cosmology and inflation. The curious thing. There are a few exact or expressions for 4-point function, but the truth is that you can kind of count them with your fingers. And here I mentioned some expressions. Now, Hartle-Hawking, okay, so let me pause here and ask if there are any questions before making the next point. All right, so if there are no questions about this, I'd like to mention one more property about conformal field theory, or at least the structure of this Euclidean conformal group and the Hartle-Hawking wave function, namely the observation that not just the field operators themselves have nice transformation properties under the conformal group, but also the late time structure of the Hartle-Hawking or Bunch-Davies wave functional at late times has a structure which is nicely governed by the symmetries of a conformal field theory. And another proposal to relate conformal field theory to the wave function goes under the lines that this wave function, which is another natural object under conformal symmetries, is in fact computed alternatively by the partition function of the CFT itself. So this is the other main proposal of using conformal symmetries in the context of an asymptotically de Sitter universe. And the picture is that somehow the calculations that we do in the bulk, which involve integrating vertices across all times, are equivalent and in fact perhaps even defined by a calculation where you only take the late time slice and you compute on it expectation values within a timeless conformal field theory that involves no time at all. So the point here that I'm making a little briefly is that all of these ideas point toward the possibility that there is some sort of relation between exponentially expanding spacetimes, particularly if they're eternally or very long-lived de Sitter universes, and the concept of some type of conformal structure. Now, whatever this conformal field theory is, perhaps in parallel to some of the discussion of Andrea earlier on flat space lography, is that whatever this structure is, we shouldn't really view it as a conformal field theory in the traditional sense. That is to say, something satisfying a standard state operator correspondence with a standard select collection of local operators and a standard reflection positive structure. It's really more of a conformal operator algebra or some more abstract notion of a conformal structure. And as far as I can tell, in order to properly conjecture the idea of a DSCFT, one has to go back for a moment and likely address questions regarding the nature of gauge invariant observables in the future boundary and the proper measure for the square of the wave function. What is it that we should integrate this wave function squared against? And relatedly, and perhaps more ambitiously, what is the nature of the microscopic Hilbert space and operator content ascribed plus? Particularly remembering the point I made, thanks to Gaston's question, that we need to gauge everything, including the isometries of the Disidio space in a theory of gravity. Similarly, the notion of unitarity that's relevant to the problem in this context is different from the type of unitarity that we like to impose in our traditional computations of conformal field theory. Because in our traditional calculations of conformal field theory in Euclidean signature, the way we choose hermiticity conditions is related to the requirement that the theory is unitary in Lorentzian signature. Over here, however, the Euclidean conformal group is already relevant to the Lorentzian spacetime itself from the get-go. And so we have no reason in this case to choose peculiar reality conditions for the CFT that have to do with some Wick rotation to Euclidean signature, because the theory, the conformal structure, whatever it may be, lives inherently on a Euclidean slice, which is a constant time slice of a Lorentzian spacetime. And this point has been recently addressed and starting to be appreciating with work amongst various people participating in the audience. And I think it has a nice, it will have a nice evolution, because it's really putting the group theory of the problem in its appropriate context. These are difficult issues, of course, but perhaps in simple enough mathematical models or exotic enough models, some of these issues might have a chance to be addressed in a concrete and sophisticated fashion. Okay, so are there any questions about this discussion so far? Because at this point, I've said what I had to say about these kind of global pictures, and I'd like to proceed to some aspects of the Disidio horizon. And so I'm going to stop for about 7 seconds to see if there's any questions about that, and the understanding that I'm going to move on to a logically different topic.
So you mentioned that the Bunch-Davies the Hartle-Hawking wave function at late time transforms as a partition function of a CFT. What are the operator insertions in this context? And
for the wave function picture, you mean?
Yeah.
Yeah. So the wave function picture, the argument of the wave function, of course, this is a choice of basis, like for any wave function. But there's a natural choice of basis, which is given by the late time profiles of the fields themselves. So generally, if you wait long enough, your field will have some late time profile, and you can compute this is like the field eigenbasis. You can compute your quantum state in a field eigenbasis, and it becomes a functional of the late time profile of the field. And so just like in quantum mechanics, you have psi of x. In this context, you have, say, psi of g, where g is the induced metric on the late time surface.
Okay.
Does that answer the question?
A potentially stupid question. Well, what are the related scaling weights of these field insertions?
Good. So that depends on what representations the field transform under, at least in the free level.
Right.
And so they can vary. Yeah.
Okay.
For the late time profile of the metric itself, the scaling weight is simply 0.
Okay. Right.
Because it's the source in the ADS-CFT language. This would be the source of the stress tensor, which is a marginal operator.
Thanks.
Yeah.
Also, Andrea Poom raised her hand. She has a question.
Hello?
We don't hear you.
Okay, now?
Yes.
Yeah.
Okay, so on the last comments that you made. So in flat space, the Hermitian conjugation relations that you would get from the bulk are different from the ones that you have in radial quantization. But recently, people made progress in trying to put this into more the form that is used that you get in radial quantization by using shadows. Has anything been tried in Disidio to make things look more like using shadows or light rays?
The closest I know is an attempt to express quantities in Disidio in terms of a discrete basis, which seems to be related to something called quasi-normal modes in Disidio. And for that, I refer you to these papers, to this paper over here. Yeah.
Thanks.
But this is the ongoing part of the ongoing discussion about these kind of things. This is very fresh questions, good questions. Okay, so good. All right, so now then we'll proceed to the next portion of the discussion, which is the Disidio horizon and the Euclidean sphere. And this picture over here is quite nice because it's a picture that was drawn by Disidio students, where you have Disidio and he's creating a sphere. And so it's a wonderful picture. I don't quite, well, the quote, we don't have time to discuss. Okay, so let me discuss this Disidio horizon business. Now, first of all, I should explain why it's even conceivable that there is a notion of horizon in this context. After all, cosmology is the opposite of a black hole. A black hole is a matter collapsing into a singular region of space, shielded by sort of a horizon, whereas expanding space is the opposite. Nonetheless, if space is expanding fast enough, it could so happen that the light emitted by galaxies cannot keep up with the rate of expansion of space, thereby creating the possibility for a region of the expanding space to shield itself away from any reasonably local observer. And so for that reason, if space expands sufficiently fast, it seems to be connected to the physics of horizons. And in fact, this is precisely the case, and how it was originally discovered by Disidio, because Disidio permits a static coordinate system for a portion of its complete space. And this is known as the static patch of the Disidio universe. And it looks a lot like the Schwarzschild coordinate system of the Disidio universe, of a black hole universe. Now, the metric I've chosen to write in the following coordinate system has a coordinate psi, which is like a radial coordinate. Here, psi ranges from 0 to pi over 2. And then you have a region, psi equals 0, where the t component of the metric vanishes. And so you have a horizon. So this would be psi, it puts you in here. And then you have a celestial sphere, what Andrea would call a celestial sphere over here, it's d omega over here. And the celestial sphere is largest at the horizon over here, where psi equals 0, and shrinks to a point at the origin of the space where the sort of natural inertial observer experiences their world. Okay, so we have this description, and indeed you can see in the Penrose diagram very manifestly that there's events in a large portion of the space-time that are forever causally disconnected from the experience of an inertial observer. Okay, and so we have a horizon, and a lesson, it seems to be an important lesson, that when we have a horizon that is created by the space-time itself, as opposed to, say, the observer themselves, we might want to take such a horizon seriously. Yes, and so we can now ask ourselves questions about the nature of this cosmological horizon. Yeah, and I should say that, interestingly, in the limit where the Disidio length tends to infinity, just to connect to other talks, to lambda equals 0 talk, this horizon, in the limit where the Disidio length tends to infinity and the Disidio universe tends to a flat space, in fact becomes the null boundary of flat space. And so there seems to be it's sort of as if, from the point of view of flat space, we've brought in the null infinity of flat space into the form of a finite size horizon. I don't know what the implications of that picture are, but it seems to link in an interesting way the null boundary of flat space and the Disidio horizon.
Okay, but I think it's important that the cost to do that is that it becomes observer dependent.
This horizon is observer dependent in that each observer will observe their own horizon, but it's observer independent in the sense that all observers will observe a horizon. This is the cosmological version of the fact that a black hole horizon is observer dependent in the sense that an infalling observer observes no horizon, whereas an observer accelerating outside of the black hole horizon observes a horizon. Yeah. So now the presence of horizon suggests, and I think this is a very important question, that there might be some association to what people like to call holography, in the sense that this horizon may carry information, may carry some sort of information, entropy or something. This is a far less clear and far more open problem than the case of black holes. And so far there exists no clear argument as to why and in what form this information is contained. And so I think it's a crucial problem, since it ties together, whatever this entropy is, it ties together the cosmological constant, h bar, the Newton constant, the speed of light, all in one formula. And so it would be interesting to understand whether or not this is truly encoding some form of information. Because if it does have an entropy, this entropy is significantly larger. It really dwarfs all of the remaining entropy in the universe, including that of supermassive black holes at the center of galaxies. So this is pertinent, and perhaps a dimensionless way to ask the problem of what is the cosmological constant is to ask the question in a dimensionless way, which is, why is the value of the Disidio horizon entropy so large? Or what is it counting, and is it natural or not that it's counting something with so many states? Okay. So now I have one more qualitative slide about Disidio horizons, and then I'd like to discuss some more quantitative features of this horizon. But before we conclude too much about the nature of this horizon, I think it's extremely important to compare and contrast properties of Disidio horizons compared to black hole horizons. And though naively it may seem that they have some similarities, for example, they obey some sort of first law in the same way, and they exhibit some sort of exponential decay of excitations, they are also distinguished from black hole horizons in qualitative ways. The nature of very heavy particles seem to be less and less sensitive to the presence of a horizon in the context of the Disidio horizon. The Compton wavelength shields itself almost completely away from the Disidio horizon. The response of the horizon to localize the pulses or shock waves or other things due to the theorem of Gauss and Walds is opposite to that of black holes. In fact, basic geometric features like the connectivity of geodesics at large spatial separated points is absent in the context of Disidio horizons, as opposed to black hole horizons, where you have real space-like geodesics that grow continuously as you consider the points to live further and further in the future. This is related to these questions that Gabor discussed to some degree. And this is nice discussion by Saskin and Galante, Chapman, Kramer. Okay, now, okay, but having said all this, I think it's important, because we don't have as many quantitative holds on what this horizon is and what kind of things it computes, to try to see how much quantitative information we can extract about this horizon. What kind of calculations can we do in order to quantify and characterize the nature of this horizon? Okay, so I'm going to dedicate some time now in the talk to try to quantify some of the thermodynamic features of this horizon as perceived by quantum fields propagating in this region of space-time. But before doing so, let me pause and see if there's any questions. Okay. So then I'll proceed. And the way we're going to proceed now is...
I have a question, and it's very basic. No, it's very basic. Suppose you want to play the first law in the Sitter space. We know that in that case, you can think of a kind of back reaction if you change the mass of the mass inside. Let's say you consider black hole inside the Sitter, and then the change of the variation of the mass of the black hole is related to the variation of the horizon size, if you can imagine such a Gedanken experiment. But I want to understand physically what it means quasi-normal mode, because in the case of the black hole, this is pretty clear. What it would be, I mean, naively, I would say in this case it would be the same, would be a perturbation of outgoing modes at the horizon and certain smooth conditions in the bulk that just matter going out. That's the point. Or?
Matter going out. So you say, you set up an experiment where you say, I want, sorry. So you say, I want to send a pulse, yes, and I choose boundary conditions so that everywhere else in the space, the field theory is smooth and that there's a purely outgoing condition of the quantum field. And I want to measure the response at a later time of the pulse that I sent out. So there will be dissipation because there's a horizon, but you will measure a Green function, which is a function of the time separation in this experiment you made. And one way to define these quasi-normal modes is as the poles in the frequency Fourier transform of this Green function in the complex frequency plane. They are just characterizing the dissipative features of the horizon. And indeed, the boundary conditions are those that you mentioned, namely that it's purely outgoing and almost everywhere smooth except at the singular point of the excitation. Okay, so now we're going to enter the range where we would like to compute in more detail some features of the Disidio horizon. And in particularly, we are going to permit ourselves to compute these things in Euclidean signature under the assumption that the Euclidean path integral is at least semi-classically meaningful, and under the hypothesis of Gibbons and Hawking that the Disidio entropy is defined by the following path integral, namely the path integral where we somehow sum over compact topologies of a gravitational path integral weighted by the Euclidean gravity action and any other Euclidean matter fields that might be present. And the reason that we sum only over compact manifolds is that the Euclidean saddle associated to Lorentzian Disidio is the round sphere, and the round sphere is naturally lives on the spherical topology, which itself has no boundaries. And so Gibbons and Hawking proposed that the definition of the Disidio entropy is nothing more than the gravitational Euclidean path integral over compact manifolds. The reason usually this is a free energy. The reason it's not a free energy in this case is that in Disidio, where the Lorentzian picture is on a compact spatial slice, there's no natural boundary where we can put an ADM type of energy to define an energy. And so if you have general relativity on compact spatial slices, the energy vanishes. And so if the free energy is E minus T times S, and E is 0, all you have left is the entropy. And so Gibbons and Hawking proposed then that the definition of the Disidio entropy is the following. And what's nice about this formula is, or it's a proposal, is that it's at least, it's diffeomorphism invariant. And in fact, it's field redefinition invariant as well, if treated in a semi-classical way. And so this is a very nice object to try to understand and see what kind of features and what kind of quantum corrections the entropy one can produce due to the fluctuations of fields about the semi-classical Disidio saddle. Okay, so we're going to explore this proposal for the Disidio entropy and see whether A, it makes sense. After all, it's a rather abstract notion, yes, and B, what can be computed about it, at least at to low orders in the loop correction. And so we're going to spend some time computing this object. But this is the basic conjecture. This is the Gibbons-Hawking Euclidean path integral as a starting point to compute quantitative properties of the Disidio horizon. And let me make the case for the Euclidean signature in one more way, because it's important, I think, to not forget about the global picture. But there's this type of Euclidean democracy going on in
Can
the
I ask a
context of
question?
Disidio. Yeah.
So could you comment a bit on how do I interpret that entropy conjecture, like in say the flat space limit?
Hello?
Sorry, could you hear me?
Yeah, I can hear you now.
So could you say a bit about how to think of this entropy formula, but in the flat space limit of the Disidio?
No, I can't. It's an interesting question. I will comment on that in Gather Town.
Thank you.
Yeah. Okay. So, but the Euclidean democracy is the following: that in fact the round metric on the sphere I mentioned is the continuation, is the Euclidean continuation of the static patch, where the Disidio horizon becomes some region of the sphere. But it's also the Euclidean continuation of the global metric of Disidio. Sorry, that would be this. And so somehow the Euclidean sphere and quantum field theory in the Euclidean sphere packages in a rather non-trivial way information about both the horizon picture of Disidio as well as the cosmological picture of Disidio. It's kind of democratic, and it just rests on how you ask questions, which picture you have in mind. Okay. Now, the first question we can ask to test the idea of Gibbons and Hawking in a meaningful way might be, okay, let's consider the following setup. Let's consider we have a quantum field that lives in the Disidio background, and let's compute the sphere path integral of this quantum field, okay, even at the free level. Now, this has been a calculation that has been done historically in many different contexts for many different reasons, but usually the result is left at an answer that involves some unusual numbers or zeta functions, and it's not really expressed in a natural Lorentzian way. The sphere partition function is a rather exotic object, but equipped with a picture of the Lorentzian Hilbert space, particularly with the group theoretic tools that we discussed, and the characters and Harishchandra's picture of these representations, we can ask whether we can express the path integral of fields, of freely fluctuating fields in a fixed Disidio background, in terms of the group theoretic quantities that stem from the mathematics literature. And indeed, to make a long story short, the answer is affirmative. And one can express, even before we do any gravitational path integrals, the field theoretic path integral in a standard canonical ideal gas type expression. So if you exponentiate z, you have the standard sort of e to the minus beta omega over 2 divided by 1 over e to the minus beta omega product over all omega in quotation marks. And the crucial component to be able to understand the sphere partition function as a Lorentzian thermodynamic type of ideal gas calculation is the fact that the continuous spectrum in the static patch, which stems due to the presence of horizon, is properly treated with a measure. And the measure is some sort of density of states, which is precisely the object that Harishchandra computed when dealing with the continuous unbounded character calculation that he had to take the trace for. Okay, and so it's for spin 0 and spin 1/2 fields, one can simply prove that the sphere partition function that we've been studying in all sorts of contexts indeed permits an ideal gas canonical type of expression in terms of the spectrum of states, the continuous spectrum of states in the static patch Hilbert space. And this is an alternative expression to the type of expression we often have to impose in the black hole quantum field theory in the presence of horizon, which is known as the brick wall boundary condition, where we put a Dirichlet condition to tame the continuous infinity very near the black hole horizon itself. More generally, one can explore this problem for arbitrary spin S fields. And in particular, one derives a very similar expression, which I've written here in terms of a Fourier transform of the density of states. So that it's written in terms of this character I wrote earlier as a function of math frac T. And the expression for higher spin massive particles takes essentially the same form as an ideal gas thermal path integral, except that there's a small correction to this expression that involves another Disidio group character, but one that lives in 2 dimensions less than the 4-dimensional character itself in the case of d equal 3. And this correction has appeared previously in different forms, but it's effectively related to the idea that there may be edge modes localized at the horizon, which is a codimension 2 surface that need to be taken into account in any proper treatment of thermodynamic contributions of horizons. And so the advantage here is that we have these expressions written in a rather covariant and group theoretic formalism. Okay, so to some degree, the conclusion is that at least for quantum fields in a fixed Disidio background, this rather esoteric Euclidean sphere path integral seems to admit a rather natural looking expression in terms of a continuous Lorentzian Hilbert space of modes in the static patch geometry itself. And this is useful because it gives us some faith that this Gibbons-Hawking path integral is indeed at least at the level of quantum fluctuation, something associated to thermodynamics. Okay, so that was the point of this slide. And if these expressions seem a little bit abstract, hopefully this expression does not seem abstract, but to make the discussion even more concrete and to show the sort of technical value of these kind of expressions, I can give you an example, which is that in 4-dimensional, just to give you a physical example, in 4-dimensional gravity, we can ask what is the one loop, up to one loop, what is the 4-sphere path integral about the 4-sphere saddle in Einstein gravity in 4 dimensions. And this is a question that has been asked for a long time. And there are various proposed answers in the literature and various different pieces missing from each answer, but at least in this formalism, the expression is transparent enough and computable enough that one essentially finds the clear answer. And the answer contains various different features. S0 is just the leading semi-classical saddle, which is just the area of the Disidio horizon over 4G. That just comes from the round sphere saddle itself. And then there are certain logarithmic corrections, essentially 2. The first logarithmic correction comes from the fact that when you path integrate a gauge theory on a compact space, you have to divide, not forget to divide by the residual volume of the gauge group, the constant part of the gauge group, which is no longer killed by the presence of boundary conditions. And that gives rise to a contribution to the path integral, the sphere path integral, that is of a group theoretic nature. And the 5 over here is nothing more than 10 divided by 2, where 10 is the dimension of SO5. And the other correction is more analogous to the heat kernel type logarithmic divergence that you get in local quantum field theories. And the coefficient was well known in the literature, and one can recover it in this picture using Harishchandra characters, using a simple calculation of the integral. And finally, there's a constant term and a phase. The phase has to do with the fact that when we compute Euclidean path integrals, we have to analytically continue certain contours of integration. Okay, so the point is that the structure, at least in the semi-classical approximation of this gravitational path integral, takes a very specific form, and it's the kind of form that we'd like to understand in generality. For instance, this piece is rather specific to the Disidio problem and is not necessarily present in the general context of black holes, another distinguishing feature between black holes and Disidio. So now, in the last part of the talk, I'd like to make some comments about understanding the Gibbons-Hawking path integral in a more concrete form. And in order to do so, in the absence of a clear path provided by approaches to quantum gravity, standard ultraviolet completions of quantum gravity, we're going to allow ourselves to veer off into the exotic world of lower dimensions, okay? And I'd like to just make a few comments about the three-dimensional case and a few comments about the two-dimensional case. And again, what we have in mind is whether we can recover these kind of structures in theories where we have more theoretical control, and whether we can control the path integral that Gibbons and Hawking instructed us to compute in a more theoretical, with more theoretical control. So let me start with some comments on three-dimensional gravity. In three-dimensional gravity, the basic tool we have at our disposal is that the theory is renormalizable. We can treat the ultraviolet structure of the theory being topological in a rather clear way. And there's a connection to Chern-Simons theory, at least at the semi-classical level, that permits us to ask the three-sphere partition function in a very concrete language. And just to give you some more details, in Lorentzian signature, for positive cosmological constant, three-dimensional gravity as a Chern-Simons theory, as many of you know, it can be expressed as follows, where the gauge group is has the peculiar and somewhat complex, difficult feature that it's non-compact SL2C gauge group, Chern-Simons theory. And in Euclidean signature, the theory is a gauge theory with SU2 gauge group, but the unusual feature from the Chern-Simons perspective is that we're dealing with a complexified level, okay? And so the Gibbons-Hawking path integral in pure three-dimensional gravity is the question of whether we can compute, provided the picture of Chern-Simons theory is correct, whether we can compute on a three-sphere the path integral of Chern-Simons theory and obtain an interesting function of the level. But the three-sphere path integral of Chern-Simons theory is an object that has been heavily considered in the context of standard Chern-Simons theory, and there exists rather analytic expressions which, under certain assumptions about the analytic structure of these expressions and the fact that there's no non-trivial flat connections on the three-sphere, permit an analytic continuation into the complexified complexified levels. And so there's a rather natural object that we can compute, which is or a natural conjecture that one can make using these tools, which is namely that the all-loop three-sphere partition function that Gibbons and Hawking wants us to compute in the context of 3D gravity is given by the following formula. So this is this is an exact, the proposal is that this, once we fix the three-sphere, this is an exact expression for pure quantum gravity, for pure gravity in the semi-classical limit with all loop corrections on a three-sphere. And so we can now ask the question, not just at the one level of whether the quantum corrections can be interpreted in a thermodynamic way, but rather at the all loop level. And indeed, there's a semi-classical limit given by large K, which is equivalent. Yeah.
I suppose the quantization condition for lambda comes from the fact that SU2 is a compact group, right?
Yes, yes.
So what's special about lambda equal -2 that permits you to write down such a nice expression?
So lambda is a coupling that the theory permits,
but any integer number, but you gave the expression there for 2.
Oh, this has to do with a little bit with how one regularizes the theory. So at kappa equals 0, just to be clear, at kappa equals 0, this is the standard Chern-Simons theory. And this is the dual Coxeter number of the SU2 group. We typically write things in terms of k plus 2. So
lambda is a kind of level or something.
Lambda would be the level of the Chern-Simons theory, which when kappa is 0 is just an integer. So this is analytically continuing the standard expressions of Chern-Simons theory away from lambda.
Exactly, that's my point. Usually the expression when the label is like minus the Coxeter number is a kind of special, right?
Well, here, what would be special about it, I think, is that would be a regularization scheme where the parity odd part of the gravitational theory has 0 coupling.
Okay.
Yeah. You see, lambda is associated with the parity odd part of the gravitational theory, which is the non-Einstein part. And I think you have to sort of define what you mean by the coupling of that theory. And the coupling of that theory is naturally lambda plus 2. I think that's my suspicion, but okay, but don't quote me on it. All right. Now, okay, so the point here is that we've afforded ourselves an expression where we don't just have sort of a one loop picture, but an all loop picture of the gravitational corrections. And we can ask whether there exists a Lorentzian interpretation of such an expression. And here we can draw inspiration going back to ordinary Chern-Simons theory with a compact gauge group and the integer level from literature that's known in the condensed matter community as the topological entanglement entropy literature, where the analogous expression of the Euclidean 3-sphere path integral of Chern-Simons theory was associated to a very natural thermodynamic computation of an edge mode theory that lived at the boundary of the disk. And the picture that they have is that in Lorentzian signature, the topology is a 2-sphere times time. And we split this 2-sphere into 2 disks. And now there's some sort of edge mode because it's a gauge theory that lives on this disk. And we can try to assess the entanglement properties of these edge modes. And under certain assumptions on how to treat entanglement entropy in gauge theory, namely some sort of extension of the gauge invariant Hilbert space when you cut through the links of the gauge fields, one can really reproduce the detailed form of this function in the language of what's people call the modular S matrix of the chiral Wess-Witten model. Okay, this is technical language, but the point is that there seems to be a Lorentzian picture for this type of 3-sphere partition function. And it's a very natural question that one can begin to ask whether this type of edge mode picture remains true in the gravitational context at the level of a complexified version of the Wess-Witten theory. And this is under exploration. Okay. Now, for the final part of the discussion, let me pause again for a few seconds, see if there's any questions. But then I want to go to 2 dimensions and make some statements about 2 dimensions. So, are there any questions at this point? Joris.
Yeah, I wanted to ask in the 3-dimensional case, if in any of these observables, if there's some sign of an enhancement to a Virasoro symmetry as opposed to just a group. So,
well, interestingly enough, so usually Virasoro symmetry is associated to sort of like the asymptotic symmetries or something like that at the late time boundary of the S3 because it's sort of a 2. But here, actually, because the edge mode theory is itself a chiral CFT, within its symmetries, it naturally has the Virasoro symmetries, right? In fact, it has an extension of the Virasoro. It's an affine extension of the Virasoro symmetries.
Yeah.
But rather nicely, now this Virasoro group lives at the edge of the horizon as opposed to the less physical future boundary. Yeah. So these Wess-Witten models are kind of chiral theories that.
Can you compute the central charge as you would do with the standard?
We have a conjecture for the central charge in the complexified. In the standard case, many things about these theories are known. We have a fairly reasonable guess about some basic features of these theories.
And I suppose it has to be linear with K, right?
At large K, it counts the number of degrees of freedom, so it's something like 6 or something.
So it doesn't grow.
It doesn't grow with K at large K because it's the edge mode theory associated to SU2 times SU2 Chern-Simons theory. So it's just the number of field theoretic degrees of freedom.
That's funny because it doesn't tend to infinity in the same classical limit.
But these edge mode theories are associated to the quantum corrections, not the leading entropy. So you see, in the Chern-Simons case, this term, which is the area of the horizon, is a pure phase. There's an I, and it's equal to 1. So these edge mode contributions are actually, in our language, would be counting all the loops, but not the leading piece. The role of the leading piece is to tell us how to organize the loop expansion, in terms of what parameter to organize the loop expansion. But it's far less clear physically what that piece is. That might have to do with more divergent properties of the edge mode theory. But the point is that there's many detailed features of the full loop expansion that beg for an interpretation. If you want, okay, let me reserve a comment about this related to the relation of the entropy of the zero temperature entropy of BBS black holes and the entropy associated to small excitation. And let me just plug that in the system. Okay, so then as a final remark, I'd like to mention enthusiastically, in fact, the simplest way to go down in dimension without losing the essence of the problem altogether, which would be sort of a 1D version, which is two-dimensional de Sitter problem. So here we are in line land as opposed to flat land, which is in fact the essence of the flat land story. And so I'd just like to make some remarks about controlling this gravitational path integral. Now, the path integral that Gibbons and Hawking instructed us to compute in any dimension is in fact a path integral that the community studying two-dimensional quantum gravity studied in great detail in the late 80s and early 90s, or the 80s and 90s. Because you see, it's precisely in two dimensions is the context where you can study this path integral in its most detailed and precise form, yes? Because we know what it means to sum over compact manifolds. We know what it means, we believe, according to a conjecture of Disser and Kawai and Francois David, what it means to path integrate over the measure over all metrics. And in fact, there's very nice statements about this in the presence of matter as well, and the kind of matter we're interested in, which is sort of light fields that provide the most interesting contributions to the entropy. And so this seems to be a rather interesting connection then between the world of Gibbons and Hawking and the world of 2D quantum gravity, because they were computing from this perspective precisely the path integral that Gibbons and Hawking instructed us to consider. Now, this comes at a cost, of course, because nothing is free in life. This comes at a cost, which is that these theories, unlike their higher dimensional avatars, are theories where the metric is always highly fluctuating. They don't traditionally permit the round sphere as a semi-classical saddle. And for that reason, although they may be very fluctuating versions of some type of de Sitter, they're not what Gibbons and Hawking have in mind. Nonetheless, there's parameters in this theory, and one might be interested in parameters where we can tame these fluctuations. In particular, there's a limit where we drive up the value of the central charge of the matter CFT in such a way that the fluctuations that were violent geometric fluctuations for generic order 1 values of central charge become controlled in a traditional 1/cm expansion, which is precisely of the form of a semi-classical expansion that Gibbons and Hawking instructed us to consider. And this problem comes in two flavors. This problem comes in two flavors where we can either drive the specific, the central charge of the matter CFT all the way to -infinity. These are called the multi-critical family of minimal models. They're known in great detail, their operator content, OPE coefficients and all that. Or we can drive the central charge of the theory all the way to +infinity. In both of these cases, the problem admits a saddle point perspective. In case A, where there is more theoretical understanding of the problem, in order to get a saddle point picture, one has to restrict the area of the manifold of the two-sphere to have a particular size. And this was originally pointed out by Zemanojikov and very nicely explored in a more recent paper of Beatrix where the saddle point expansion and the systematics of the saddle point expansion have begun to be studied in a very nice way. And there's a lot of details in the semi-classical expansion, and one can study those details and the coefficients that appear. It has a nice interplay also with the literature of the DOZZ formula. Expression B, the limit B is the limit in which the CFT has a large positive central charge, where less is known microscopically, as I'll mention in a moment. But also here, certainly from the gravity perspective, one can initiate a systematic saddle point expansion of the problem and start to address properties of the saddle point expansion and understand how these corrections are associated to certain properties or Lorentzian contributions to the entanglement entropy of the DS2 horizon in this case. Okay, so even though general 2D gravity is a highly fluctuating theory of a metric, we do have parameters that can drive the wild fluctuations down to a controlled semi-classical expansion, and then we can ask in the language of the leading saddle what these corrections correspond to. And so just to give you some formulas, the leading order, and to the leading topology, the path integral of Gibbons and Hawking has the following flavor, or has the following precise form. I showed you the exact expression over here, but in the large C limit, there's a leading piece which we might associate with the S0 itself, which comes from just the topology, because here the Einstein term is just the Euler character, and it looks like the leading piece, like what we call S0, the A over 4G. And then there's a logarithmic type of contribution, which is similar to the log contributions we saw in the 4D Einstein expression, which itself admits a large C expansion with corrections, with nice numbers that we can compute. And the leading number is something that those of you who've studied entanglement entropy will be familiar with from papers of Wilczek and Larsen.
Just a question. This would be the second law, right? The one associated to the entanglement. No, there is no contribution similar to the law of the leading piece, right? Because before you had two logarithmic corrections.
I would say that this is, so before I had written S0 plus log S0 plus 548, whatever log lambda.
Yes.
This would be like the second log. However,
exactly, okay. The entanglement to gravity.
Yeah. So this would be, and indeed, and the leading piece here, the C over 6 is this Cardi-Calabrese formula of entanglement entropy, but it comes with corrections. And these corrections, presumably, are due to the fluctuations of the gravitational field that correct the Cardi-Calabrese formula in a systematic 1 over C expansion, which is quite interesting that we have now a prediction for how the fluctuation of gravity corrects entanglement entropy of Cardi-Calabrese. To me, though this formula exists in the old literature, this is an exciting possible physical interpretation of their formulas. Now, and then there's this other piece, F0, which also permits a large C expansion. And in it, there is a log Cm term. And that log Cm, I would say, is more similar to the log S0 term that we discussed in the other context. Okay,
I don't want to be annoying, but just to understand this point, because this lambda is related to what you called before a 1 over lambda L sub ref. No? And this is associated to this cutoff. It's very important to understand.
No, this is so just to be clear with the notation, this is the cosmological constant of the 2D gravity theory.
Yes, but before you had it in company with the L sub ref.
I had it with the L Planck or LUV to make it dimensionless.
Okay, just to understand, because I mean, just to take seriously this next to leading correction, like this 19 over 6, you have to be very careful about what happened with this 1 over lambda if there is no correction for that.
Well, if it's the coefficient of the log, I think however you change this, the coefficient of the log is rather robust, I would say. It may infect the properties of F0.
Yeah, no, okay. Just my question is related to this. The expression you put before, it has something there, log 1 over lambda. If you go back, you will see what I mean.
So sorry to interrupt.
This one.
Mm.
Yeah.
But Is it
Okay, don't worry.
possible to slowly wrap up and leave?
Yeah. I'm happy, but yeah. So we can talk about this a little later. But I'm just expanding out this coefficient of the log over here, where lambda is the cosmological constant, and then there's this expression over here that is semi-classically computable. This F0, which the literature has paid slightly less attention to. Now, the advantage of this is that there is an alternative description of this theory. Just 3 minutes, I guess, just to make my point. Yeah, which is in the form of a microscopic matrix theory. And in fact, these type of corrections over here can be computed from the matrix model perspective, which we might view as an ultraviolet completion of the continuum 2D gravity theory, including the sum over all the topologies. In fact, it predicts that you need to sum over all the topologies, as Gibbons and Hawking suggested. And so, in fact, not only is this an idea, there's a very concrete proposal for what the type of matrix theory is that corresponds to these minimal models coupled to 2D gravity. And one can study them now from this perspective, thereby connecting the Hawking path integral to the counting from the perturbative perspective of 't Hooft in the planar expansion, the counting of multi-vertex ribbon graphs, as we've explored in recent papers with the driving force of all this work with Beatrix Muhlmann. Okay, so all I want to say now is just a minute of conclusion, if I have the time. And in there, I wanted to say that I think another problem that I didn't have time to discuss, which is the role of Adscft in string theory. I think it would be an exceptional tool to find a way to use in the context of the Disidio Adscft in string theory, and this may come in the form of constructing the Disidio vacuum in string theory, or connecting their underlying ADS vacuum that need to be uplifted via the bootstrap, discovering CFTs dual to the ADS vacuum. We uplift to the Disidio in string theory, embedding the Disidio inside of ADS to construct sharp observables near the ADS boundary to probe the Disidio horizon as a holographic liquid, or other modern holographic ideas such as Ryutaka Nagi bar chaos and complexity. Now, the conclusions that all of this draw for me is that there's a need for sharp quantitative data at the quantum level. It may bring us a step closer to clarifying interesting questions such as the Disidio entropy, which I believe are crucial for proper understanding of cosmology. Or perhaps it'll provide us a complete inconsistency, that the question makes no sense, that what Gibbon Hawking proposed or other questions are inconsistent, thereby clarifying the meaning of the swampland instead of declaring it. Uncovering the microscopic degrees of freedom is likely to be crucial to address this question. And these will require tools that go beyond those of effective field theory. And there I leave you to ponder this discussion with this picture over here, which is my current perspective of the all lambda problem. Thank you.
Okay, thank you so much. And sorry to have interrupted that question, but officially it is time for our break. We will start again at 4:45 CET, but this room will stay open in case.
I'll stick around in case people have questions, because I went over time.
Yes, but thank you so much for this very nice talk. And
thank you, Gilson, for inviting me.
See everyone else at 4:45 CET.